Hi, so in this video we're going to talk about an extension to the existing transportation model that we've covered. This extension of the transportation model tries to either maximize the minimum value of the decision variables or minimize the maximum value of the decision variables depending on what type of objective function applies to your specific example or the model that you're working on. So it can be quite useful because this method helps us identify what the maximum or what the minimum could be if we want to impose certain restrictions on our model, which cannot be formulated just in the form of constraints. So for the purpose of a max-min or a min-max objective function, just remember that we have to solve the original transportation model first, and then we modify the existing model so that we can incorporate either a max-min or a min-max objective function to the existing model. In all the LE models that we have solved so far and discussed, the objective function has either been to maximize or minimize some function of the decision variables. However, there are situations, especially in transportation models and logistics problems, where we may be interested in a special type of objective function. And the objective in these situations may be to maximize the minimum value of the decision variables, or we can also solve the reverse, minimize the maximum value of the decision variables. Now, these types of objective functions are useful when we want to reduce the variability in the value of our decision variables. I'm going to use the executive furniture company example that we also used for the transportation model to demonstrate an example for the min-max objective function. So let's look at the example. I'm going to start off with a little recap from the original transportation model that we covered under transportation models. And I'll extend this original example so that we can incorporate the min-max objective function to it. The original transportation model that we were solving for Executive Furniture Company was based around shipping quantities from the factories to the warehouses. So Executive Furniture Company has 3 factories in Des Moines, Evansville, and Fort Lauderdale. The numbers on the left-hand side of these nodes represent the supply capacities. They need to ship product to fulfill the demand at the warehouses, 3 warehouses at Albuquerque, Boston, and Cleveland, and their demand requirements each are given on the right-hand side of these nodes. The shipping routes are these arrows in our network diagram, and the number of these arrows are going to determine what decision variables we need in our model. The way we formulated our transportation model was we defined decision variables as X, I, J, where I refers to the factories and J refers to the warehouses, and our final model looked like this, where the objective function was to minimize total shipping cost, and we used the table of the shipping costs along with our decision variables to get the objective function for the total shipping cost. Subject to the network flow balance equations, we have to create one balance equation for each node in our network diagram. The first 3 nodes or the first 3 constraint equations have a negative right-hand side value. The reason for that is that these are pure supply nodes, and then the remaining 3 equations are for the demand nodes. I've shifted my screen to show the Excel solution for this transportation model, and if you look closely at the solution that Excel is giving us, the minimum shipping cost that we can achieve under this situation is $3,900, and that can be achieved by looking at these numbers for the shipping quantities on each route. So what the solution is telling us is that from Des Moines, you need to ship 100 units of product to Albuquerque, and you're not shipping anything from Des Moines to Boston and Cleveland because it's too expensive. On the other hand, Evansville is shipping both to Boston and Cleveland, and Fort Lauderdale is shipping both to Albuquerque and Cleveland. Now, let's imagine a situation where you are the warehouse manager at Boston. If you look at this optimal solution, it might make you a little nervous because all of the demand from Boston is being met by one single factory, which is in Evansville. So God forbid if something happens at the factory in Evansville and production is halted, or there is, let's say, a union strike or some natural disaster because of which the factory at Evansville might shut down, all of your demand is going to remain unfulfilled because you don't have a second supplier in this case. This is a perfect situation to apply the min-max objective function to this existing model so that we can minimize the maximum quantity that is going to be shipped on any route. Now, because we're not exactly sure what this maximum quantity should look like, whether it should be 100 units, 150 units, or anything in between, we need to define that maximum shipping quantity as a new decision variable to our existing model. So let's define this new quantity as S, and I'm defining S as the maximum quantity that can be shipped on any route. And by any route, I mean the 9 routes that we have defined earlier in our existing transportation model. So I have now defined a new variable S. What you call this new variable does not matter. It's just as long as you're consistent with the same notation, it's fine. So you can call this new variable F, G, H, just so that we are consistent with the PowerPoint presentation. I'm calling this S because it's denoted as S in that PowerPoint presentation. And S would be sort of the cap on any of these numbers here. And as our objective function, we want to minimize this maximum quantity. Because we are minimizing this maximum quantity, we need to reformulate this model with a new objective function. And our new objective function would be to minimize this value of S. Okay, so this is a special type of an objective function because I earlier mentioned that S is going to be a decision variable since we don't know what value is S going to take. S is an unknown, which is why we have to add it as a decision variable to our model. So the special characteristic of our new objective function is that it is also a decision variable. Now, this is an important point to take into consideration while you are modeling this, is because you will need to add S not only in the objective function portion of the solver, but also in the changing variables portion of solver as well. So our new objective function is to minimize S. I'm going to leave a cell blank here right in front of S so that I can store the value of S and highlight this in green so that my Excel solution can populate the value for S in this cell G18. So now that we've identified the decision variables as well as the objective function for our new model, we have to make some changes to our existing Excel template. Because S is now our new decision variable as well as our new objective function,
what do we do with the cost here? Because that was our original objective function. So in this scenario, you would usually be given some information about the shipping costs that you need to add into your model. In this case, assume that the management at Executive Furniture is willing to go up by 5% on this total shipping cost, just so that they can incorporate the request by the Boston warehouse manager to limit the quantity that can be shipped on any single route. So let's assume that they're willing to go up by 5%. That gives us a new budget for shipping costs, and this budget is 105% of our optimal solution, which was 3,900. So our new budget is 4,095. Because we're not having multiple objective functions in our model, our objective function is now the value of S. We need to incorporate this shipping cost as a new constraint in our existing model. So the existing network flow equations would remain as constraints in our model still, but we would need to add a budget constraint for this model. Just so that I can add the additional constraints to my new model, I've created a segment here which is labeled other constraint, and this is where I'll keep adding the additional constraints that I need to solve my min-max objective function. The first additional constraint that I need to incorporate is the budget constraint. So our total cost, which was earlier our original objective function, will now be a constraint in our extended model. The original objective function was a sum product of our decision variables with the shipping costs, and that's what I'm going to use as the left-hand side value for my new constraint, and this needs to be less than or equal to the new amount that I just wrote down here, 4,095. So I'm going to manually input this value in here. The reason for that is because I don't want any links in here. I don't want a formula in here for Excel to get confused. So I'm manually hard coding this value of 4,095 into my right hand side for the new constraint. Next, we need to tell Excel how S is defined to our is connected to our existing decision variables. Since we've already defined S as the maximum quantity that can be shipped on any single route, S can therefore be a value which is always higher or equal to any of these numbers here, which means that I would need to add 9 additional constraint equations into my model so that I can define S as being higher or equal than each of these decision variables that I've defined earlier. So to do that, I've added each of these 9 routes as separate constraint lines in my other constraints box, and the constraint is basically S, which is stored in this cell G18, needs to be greater than equal to each of these decision variables here one by one. The first value that I've inputted is for the route from Des Moines to Albuquerque, which is stored in cell B5. So I need to put a reference to cell B5 here. The next one, again, the value of S remains the same throughout. So just to make my life easier, I can put an absolute cell reference here and drag this down all the way till the last shipping route. My sign for all of these constraints is going to remain the same, so I will drag that down as well. However, I cannot drag this value down because I need to make sure that each of these rows refer to a separate shipping route, which is in our existing model. So I'm going to do that one by one. The next right-hand side value for B will be from Des Moines to Boston, and that is stored in cell C5. The same way Des Moines to Cleveland is stored in cell D5, and I will add the remaining decision variables based on my definitions for each row here into the right-hand side values for these 9 additional constraints. So from Evansville to Albuquerque is in cell B6, Evansville to Boston is C6, and Evansville to Cleveland is D6. The same way for Fort Lauderdale, it's B7, C7, and D7. And just to use the same color coding that we've been using so far, I will make sure that I color code the cells with functions in them with a blue color so that I can know that these values are actually functions and cell references, not hard-coded numbers. That's not true for 4095, so I'll just leave that as white. Now I have completed the model formulation for my min-max objective function. Just to recap, I added a new decision variable S, which is being stored in cell G18. This new decision variable is also an objective function, which is why I've highlighted in green. And now I'm going to get rid of this green highlight here in my original objective function because that is not an objective function for my extended model anymore. And we will solve for this minimum value of S with the existing network flow constraints, which I'm copying from the original model. And I added 10 additional constraints, 1 for the budget and 9 other which show the connection between S and our existing decision variables. So now I'm ready to go to Solver. I'll open up the solver window and make the necessary changes that I need to solve for my min-max problem. The first change is the identification of the objective function. The new objective function is now this green cell, which is the value of S. It still remains a minimum value. The changing variables will still include the yellow box, but I will add S as an additional decision variable in my model as well. This will make sure that Excel knows S is an unknown and needs to solve for it. So now let's add the other constraints. I'll get rid of the existing constraints in here so that I can add the new constraints one by one. The first set of constraints is for the network flow balance equations, which was the same from my existing transportation model. This side, the right-hand side, equal to the supply capacities and the demand. Once I've added my existing constraints, now I'll move on to the additional constraints that I've created here at the bottom of my Excel sheet. The first constraint is the budget constraint, which needs to make sure that the total shipping cost is less than the assigned budget of $4,095. And finally, I can group these constraints which connect the decision variables to our existing decision variables for S with the X's that we used in the model. So the left-hand side needs to be greater than or equal to the right-hand side here. Now that I've added all of the necessary changes to my solver window, I can hit solve and Excel has given me a solution. This max quantity that was earlier unknown to us has been capped at 102.5, which means that on any single shipping route, you cannot ship more than 102.5 while keeping the budget under 5% increase from the original optimal solution. And if you look at the yellow cells for the values of the decision variables, you'll notice that the concern for the Boston warehouse manager has been addressed. They're not only shipping getting their shipments from Evansville, but also from Fort Lauderdale, which hedges some risk against one of those factories shutting down so that not all of their demand is unfulfilled.